Single-phase line-to-line loads inherently do not contribute to current flow in the neutral conductor. This is because the current flows directly between the two energized phases without requiring a return path through the neutral. If you have multiple line-to-line loads connected across different phase combinations within a three-phase system, the principle remains the same. Regardless of which combination of loads is active at any given time, there will be no neutral current generated by these line-to-line connections. I plan to reduce the neutral conductor size to approximately 250 amps appears justifiable, especially considering the load distribution. With a total calculated load of 137 kV amps and only 35 kV amps attributed to lighting and receptacle circuits, the remaining 102 kV amps is dedicated to 208 volts line-to-line HVAC loads. These line-to-line HVAC loads, as previously established, will not inject any current into the neutral conductor. To further validate the neutral conductor sizing, let's analyze the potential maximum neutral current. Assuming a maximum demand factor of 0.8 for the HVAC loads, we can calculate the approximate maximum current as follows. Multiply the 102 kV amps by the demand factor of 0.8, resulting in 81.6 kV amps. Then, divide this value by the line-to-line voltage of 208 volts, which yields approximately 392.3 amps. A 250 kcmil neutral conductor possesses an ampacity that should be sufficient to handle this calculated current. It is important to refer to the National Electrical Code, or NEC, which provides guidelines for electrical installations. The NEC stipulates a minimum neutral conductor size of 1/0 American wire gauge, or AUG, for a 400 amp service. However, there is an exception which may apply when the calculated neutral load is significantly lower than the service's overall ampacity. In this specific scenario, where the neutral current demand is substantially less than the 400 amp service rating, a smaller neutral conductor size might be permissible. Note that the determination of this allowance falls under the jurisdiction of the local authority having jurisdiction, also known as the AHJ. It is always recommended to consult with the local authority having jurisdiction before implementing any modifications to your electrical system. They can provide specific guidance based on local codes and regulations, as well as assess the safety and suitability of the proposed neutral conductor size reduction. Consider these key factors when evaluating the neutral conductor size. Firstly, the actual calculated neutral load should be determined as accurately as possible. This involves analyzing the connected loads, their demand factors, and any potential for future load growth. Secondly, the ampacity of the proposed neutral conductor size should be verified to ensure that it is adequate to handle the calculated neutral load, even under maximum demand conditions. Thirdly, any applicable directing factors, such as those related to ambient temperature or conductive bundling, should be taken into account when determining the allowable ampacity of the neutral conductor. Fourthly, the requirements of the NEC and any local electrical code should be carefully reviewed to ensure compliance with all applicable regulations. Fifthly, it is recommended to engage with a qualified electrical engineer or inspector to review the proposed design and provide professional guidance. Sixthly, documentation of all calculations, assumptions, and code references should be maintained for future reference and to facilitate review by the authority having jurisdiction. Reducing the neutral conductor size can potentially offer cost savings, but it is essential to prioritize safety and ensure compliance with all applicable codes and regulations. Remember that electrical systems should be designed and installed by qualified professionals who have the expertise to make informed decisions and ensure the safety of the installation. This analysis provides a framework for evaluating the neutral conductor size reduction in your specific situation. However, it is crucial to consult with qualified professionals and the local authority having jurisdiction to ensure that the final design meets all applicable requirements and provides a safe and reliable electrical system. When dealing with electrical systems, adherence to safety standards and codes is crucial. Always seek professional guidance to ensure compliance and safety. Here are some additional aspects to consider regarding neutral sizing in electrical systems. Firstly, understanding neutral current. In a balanced three-phase system with purely linear loads, the neutral current is ideally zero. However, In real-world scenarios, imbalances in phase loads and the presence of nonlinear loads can lead to neutral current. Secondly, factors affecting neutral current. Factors that can increase neutral current include imbalanced phase loads, harmonic currents generated by nonlinear loads, and single-phase loads connected line to neutral. Thirdly, NEC requirements. The National Electrical Code, or NEC, provides specific requirements for neutral conductor sizing based on the type of loads served and the potential for neutral current. Fourthly, calculated neutral load. The NEC requires the calculated neutral load to be determined based on the maximum unbalanced load and any harmonic currents present. Fifthly, neutral conductor ampacity. The neutral conductor must have sufficient ampacity to carry the calculated neutral load without exceeding its temperature rating. Sixthly, harmonic currents. Harmonic currents, especially the third harmonic, can significantly increase neutral current in three-phase systems. Seventhly, nonlinear loads. Nonlinear loads, such as electronic devices and LED lighting, generate harmonic currents that contribute to neutral current. Eighthly, neutral sizing for nonlinear loads. The NEC provides specific guidelines for sizing the neutral conductor when serving nonlinear loads. Ninthly, oversizing the neutral. In some cases, it may be necessary to oversize the neutral conductor to accommodate harmonic currents and prevent overheating. Tenthly, shared neutrals. When sharing a neutral conductor between multiple circuits, the neutral conductor must be sized to carry the maximum neutral current from all the circuits. 11thly, voltage drop. Voltage drop and the neutral conductor can affect the performance of sensitive electronic equipment. 12thly, grounding. Proper grounding is essential for minimizing neutral current and ensuring electrical safety. 13thly, neutral displacement. Neutral displacement can occur in unbalanced three-phase systems, leading to voltage imbalances and potential equipment damage. 14thly, neutral isolation. In some applications, it may be necessary to isolate the neutral conductor to prevent ground loops and reduce noise. 15thly, neutral monitoring. Monitoring neutral current can help identify potential problems, such as unbalanced loads or harmonic currents. 16thly, neutral filters. Neutral filters can be used to reduce harmonic currents in the neutral conductor. 17thly, professional consultation. It is always recommended to consult with a qualified electrical engineer or contractor to determine the appropriate neutral conductor size for a specific application. These considerations highlight the importance of carefully evaluating the neutral current requirements in electrical systems and selecting a neutral conductor size that is adequate to handle the expected load. Remember to consult the National Electrical Code, or NEC, and local electrical codes for specific requirements and guidelines. Before making any decisions related to the neutral conductor size in your system, consult with a qualified electrical engineer. The engineer can perform a detailed analysis of the load characteristics, potential harmonic currents, and applicable code requirements to determine the appropriate neutral conductor size. This will ensure the safety and reliability of your electrical system. Additionally, it's important to consider the potential for future load growth when sizing the neutral conductor. If you anticipate adding more loads to the system in the future, it's wise to select a neutral conductor size that can accommodate the increased demand. This can prevent the need for costly upgrades later on. Bear in mind that the neutral conductor plays a critical role in ensuring the proper functioning of electrical systems, particularly those with single-phase loads or nonlinear loads. A properly sized neutral conductor helps to maintain voltage balance, minimize harmonic distortion, and prevent overheating, all of which contribute to the overall reliability and safety of the system. Moreover, the cost of oversizing the neutral conductor is generally small compared to the potential costs associated with an undersized neutral, such as equipment damage, fire hazards, and system downtime. Therefore, it's often prudent to err on the side of caution and select a neutral conductor size that provides ample capacity for the expected load and potential future growth. Also, it is good practice to document all calculations, assumptions, and code references used in determining the neutral conductor size. This documentation can be helpful for future reference and for demonstrating compliance with applicable codes and standards to electrical inspectors or other authorities. In summary, determining the appropriate neutral conductor size requires a thorough understanding of the load characteristics, potential harmonic currents, applicable code requirements, and potential for future load growth. Consulting with a qualified electrical engineer and documenting all calculations and assumptions are essential steps in ensuring the safety and reliability of the electrical system. Keep in mind that electrical codes and regulations are constantly evolving, so it's important to stay up to date on the latest requirements. Regularly review the National Electrical Code, or NEC, and any local electrical codes to ensure that your electrical systems are in compliance. Finally, when working with electrical systems, always prioritize safety. Wear appropriate personal protective equipment, or PPE, and follow safe work practices to prevent electrical shocks, burns, and other injuries. If you're not qualified to work on electrical systems, hire a licensed electrician to perform the work.